so now what follows is that I wanna give you some guidelines regarding that selection of modes. The discussion we kind of initiated last week. Then we're gonna really, the final thing to do before the exam is that I'm gonna explain to you one thing that is called mass invariance. But that's an interesting topic because that's the one that kind of finally combines the finite element model and multi-body system dynamics. It's theoretically a little bit painful topic, but it is also with a great practical importance. And that's about it. Now, here are just a few observations regarding the, so not yet. Okay, so here are the few observations regarding that, how is that you can select the different kind of finite elements. And when using finite element model together with your multi-body simulation, typically there is no great limitation when it comes to selection of elements. In the finite element theory, there is a lot of different kind of elements available. Typically, the most often used elements that are combined together with the multi-body simulation are solid elements and plate elements. And it's actually my understanding that most of the models at the moment, the people are using solid elements. The structural elements, which is a family of beam elements, plates, and cells, those are not that frequently used. Only in certain applications you're using beams, plates, and cells. But often, just because of the simplest possible way is that mesh everything with the solid elements. Those you can use with when you're combining your finite element model with multi-body dynamics. Now, beam elements, they are typically quite simple, and it's even possible to use landmass approach when you have a beam-like structure. Of course, it's computationally sometimes quite heavy, but if you just have a simple straight beam structure, often you can simply use a landmass approach. Now, whenever using Craig puncture modes, you will get these approximate free modes. These rigid body modes that will be in the very beginning of the set of modes, those need to be eliminated because reference coordinate system will take care of your rigid body modes. So now if I would ask you why the rigid body modes need to be removed, the answer is that because reference coordinate system will take care of the rigid body modes, the rigid body translation and rotation. Now, then, as mentioned here, usual elements that are used in a structural strength analysis, they can be used typically without any kind of modification to describe flexibility in multi-body system dynamics. Now, here's an example, and I guess that you're not really familiar with this, but sometimes in a finite element community, there's it makes sense to use a symmetry models like 1/2 of the model, 1/4 of the model, and so on and so forth. Those you cannot use as a part of the multibody, and that's simply because it's going to be very hard to get the inertia correctly if you have a symmetry model. So it's recommended to have a full model without any kind of symmetry boundary condition. That's just the easiest way to go. Now, all right, so then let's look at those selection of modes in a second or the next. But prior to that, I have one in-class quiz, which is in the floating frame reference formulation, rigid body modes need to be removed because rotations are assumed to be small, deformation are assumed to be small, reference coordinate system takes care of the rigid body motion, damping is assumed to be insignificant. Okay, so let's take a look. So I have it here, so it's already available. Okay. So take your time. Okay, so let me take a look. Not here, but here. Okay, what was the number of students last time? Was it 26? 25. Okay, so one is missing. Maybe the missing one is the one that was voting incorrectly. Let's hope so. Okay, so can I just leave you guys to think, or is this all clear to you? This is as clear as it gets, pretty much. Okay, so let's, I guess this is online participants. All right, it comes in a minute or so, so let's get back to this in a bit later. Okay, so, and here. Okay, now this is this is all related to Atom software, because we've been using Atom software in the previous years, and now it's the same kind of concept works for any other kind of multibody code, you know. But this is just an example how is that you can create the different kind of models for sets that you can use in Atom software. And again, Atoms is one of the software that is based on multibody system dynamics, and floating frame reference formulation is a method how they describe flexible bodies. You know, this is the simple thing that in a finite element model, once you have your finite element structure ready, then you can simply type the script, and the script is computing everything to you automatically. And typically the scripts that are connecting finite element software and multibody system dynamics, they are based on Great Bumpton blocks. So the Great Bumpton is very often used. And it goes simply that you type like, what is the software you want to go? Here's an example, is Atom software. Then you're telling how many modes. And those are modes that you're computing using this fixed boundary condition. And then you can send also the information about the strains and stresses if you want. We can take a look at that a bit later. And then you get all your information to a multibody code. And in a multibody code, you often need to simplify your geometrical representation. And that's simply because if you have full-size finite element model, there is a huge number of geometrical details. And those large number of geometrical details make it difficult to use as a part of the multibody code. So there are techniques that you can actually reduce the geometrical representation without losing any information. It's just how is the appearance, no information lost. So you can simply make it, if the mesh is originally like the one is shown here, this one here, so you can make it just to reduce. Here in this case makes no difference, but if you think about the car body, with a very detailed mesh, it actually makes a big difference to use this simplified geometrical representation. Now, whatever you're converting or sending your finite element model to your multibody model, you're using the landmass representation. We haven't really discussed much about this, but the landmass representation means that you are assuming that your mass is distributed within your nodes. And in this representation, there is no inertia associated to rotational degrees of freedom. This is just a minor detail that sometimes cause a little bit of problem, particularly if you wanted to look at the simple straight beam-like structure. Problem is this: so if you have like straight beam-like structure like shown here, and when you're comparing the eigenvalues, there will be no inertia associated to rotation of the structure around its own axis. So that will be with the zero inertia. In dynamics, if you have something with a zero inertia, that's not good, because then acceleration goes to infinity immediately. So you cannot use anything like that. So you either, to get rid of this problem, you either have to use the solid elements, like is the case of showing here. So this is a rotating structure that is meshed by using solid elements. then the inertia will be with no problem, or you have to create artificial inertia to this axial direction. Artificial inertia could be simplest possible thing is that you move one node here a little bit, just a very small amount in a transverse direction, and that creates the inertia properties around the axis itself. So then it's no longer exactly zero, but it's having a small value that helps to compute some of the cases. Now, selection of deformation. This again is an example that is from Adams. So typically the first really the good way to select the modes is that you should take a look how is their physical appearance, if they are really making sense to use it or not. And you can animate it by seeing like what's the deformation, what's the direction that the deformation takes place, and think if your loading is in that direction or not. Because of course if you have, say, a beam-like structure or the simple structure like this, which is loaded in this direction, of course it's not making sense to have the modes that are off from the plane. You should have it just maybe a few of them, but not more than a few of them. Of course in this direction it makes sense to have them a lot to have accurate representation. But simply it is a matter that you can visualize it, and based on your engineering sense you can select the ones that you think are the most desirable. This is the one that is based on experience. So once you have a good experience you can start doing something like that. And if not, then there is a tool which is called as automated mode select. And this is something that I need to explain how it goes. Well, it goes such the way that you first computing your flexible body by using as many modes as possible in terms of reasonable CPU usage, meaning that you're adding pretty much everything you have and pretty much everything you may think that are important. And now once you have this ready, then the software will compute you the entire strain energy associated to your flexible body. How it goes then? Well, the strain energy, the definition of strain energy is 1 divided by strain vector multiplied by matrix of elastic coefficient and the strain vector again. So this is how you can get the strain energy. Alright? Now the strain a few weeks back. Okay, so we don't have any more of these nodal degrees of freedom, but we have modal degrees of freedom. What's the relation between nodal and modal degrees of freedom? Well, deformation modes. So this could be written, is this still visible? I think it is. This is this deformation mode. The matrix that includes all the deformation mode and corresponding modal coordinates. Now the modal coordinates are the one that you're solving from your multibody code. So using this relation you can estimate how much is the total energy. And then you will get the number, that the number is say 100 units. Let's not think about the details more than, let's say it's the 100 units. Now this 100 units can be then later broke down such the way that we can look how much each one of the modes or the modal coordinates will contribute to these 100 units. And typically it looks like, I need to take this, where can I make a nice drawing? Maybe here. Not here, there is not enough space. I gotta make it here. So hopefully this is clear enough. I'm gonna make a figure to make it more readable. This is mode ID number. So just a number that is associated to each one of the modes. This is my entire strain energy, and then I'm looking how much each one of these modes will contribute the entire energy. And it's typically such the way that the first one is contributing this much. Second is contributing maybe a little bit more, like this much. Then maybe a little less, like this much. Then really a lot. And the idea is that once you combine these pillars together, you will be here. Alright? then some point, some of the modes will contribute just a very, very little. And their contribution is almost insignificant. So it's something that you cannot even see their contribution. And now in this automated model selection, you're actually telling that once they're contributing less than a certain threshold value, then automatically ignored. Threshold value typically, like in this case here, the threshold value is set to be such that if they're contributing less than this much, forget about it. That's what happens. Now, this is an automated way, and it guarantees that you don't lose much of the accuracy. Problem here is that you first have to have a lot of modes to compute it correctly. And that's what makes it a little difficult to use, a little cumbersome to use. Another problem is this, that the selection of modes is always related to how you're using your machine. So if your work cycle is something that you're moving dirt here to here, then you can select just a few numbers of modes to do it correctly. But if you're changing your work cycle, you should do the selection again. So that's the problem. So why so serious today? Well, of course it's Monday and all that. But any other reason? Is there some bad news? Or it's just that it's Monday? Because of that noise?
Yes.
Ah, so you've been listening to that noise all the time, not me. Is it coming? Where that is coming? It is true that it's a little bit annoying. Can I take it off here? What kind of noise is that? This is like a loudspeakers. It is true that if I take this one, nothing. Huh. You sure they're coming from the loudspeakers?
Yeah, speaker.
How can I put it off? Maybe if I muted them completely.
Yeah, just mute them.
Here.
It is not related to the streaming.
So the good news is that it's not related to subject matter. So it's not automated that if it becomes painful, then it start to make this noise. It's not that. But something else, I don't know what it is. Really don't know what it is. Oh my God, is this much? So I realized that we are a little bit behind the schedule. That's because this is your responsibility, by the way. You need to make sure that if I start to be slow, you need to raise your hand and say, Aki, please, speed up. You know, this is just too slow. Speed up, speed up, speed up. Maybe we can make a language like this. This means speed up. Or slow down. That's going to be too complicated for me to understand. Okay, the damping, that's just that can be added to, and it could be function of the natural frequency, which is typically something quite good. So it helps to get the good, accurate models. Here are the few verifications tips, and then we're going to move on to final subject matter, which is this mass invariance. How you can verify your flexible body. First, three tips that are listed here. First of all, is that it makes sense to compare the inertia from your original finite element model and the multibody model. Why is this? Because often you may have a conflict in your units, and your body may weigh 100 kilos in a finite element model, and when it comes to a multibody model, it weighs a kilo. These are the typical mistakes. So check how much they weigh. Now once you have checked that, then compare eigenvalue results from free modes in a multibody code against your finite element code. And then finally you can set the simple numerical experiment where you attaching your structure to ground and you're measuring the deformation in the static cases. So those are the three advices that helps you to build or verify your model in a way that you are not making any systematic mistake in, say, units or model itself. Okay, but now the final thing, mass invariance. And this is the last thing that will come to exam. And what is this mass invariance? You know, again, here's a big picture. So we're using this kinematic notation to describe deformable bodies. And now this one here, this nodal or this deformation is described by using these assumed deformation modes and corresponding modal coordinates. That's how it goes. Now, surprisingly enough, there is possible that the coupling between deformation and reference motion could be very close, or it could be something that you can get rid of that coupling completely. And that coupling is defined by mass invariance. Again, what is a reference motion? The reference motion is the one that is described by this coordinate system, and it means large translation and large rotations. Deformation is something that you are superimposed with that reference coordinate system, or the motion of the reference coordinate system. Now, these two things can be separated completely, or then they can be completely coupled. How much they're coupled or how much they're separated, that all is defined by mass invariance. And as the title implies, mass invariance is a component you use in your mass matrix. But you know, there have to be some point where you do this coupling. It could be in elastic forces, it could be in inertial forces, but in a floating frame reference formulation is in inertia. And that's why the mass invariance is telling how tight is this combination. Now, this story is as painful as it gets. This is like extremely bad story. But again, let me remind you, the aim of this painful story is to see how well these two things are coupled, reference motion and deformation. Right? So let's use these kinematics, this one here. Let's use these kinematics to describe, you know, how is velocity, acceleration, and then build description of inertia. Now this is how the kinematic looks when I'm using modal coordinates. Modal coordinates. So I have here my unknowns. So these are my unknowns. These are the ones that I will solve. Modal coordinates. All right. So my vector of generalized coordinates in planar case for one body consists of translation and rotation, reference translation and rotation, and then modal coordinates. All right. So that's how it goes. In spatial case, same stuff, but we have more coordinates. So we have 3 translation, 3 or 4 rotations, depending on the description of rotation, and then we have a certain number of modal coordinates. Okay, that's how it goes. Now, if I would, and again, I need to apologize, and you need to be aware of this. So, what comes in the next slide is the scariest thing that you have ever seen in your life. Seriously. So it's all right to scream and cry. So it's all right because it's scary. It's simply scary. But we're gonna just pass this scary stuff to see how is this coupling. That's what we're gonna do. All right. So now, how is a velocity then? Well, velocity we can get by differentiating the position once with respect to time. When expressing that with help of generalized coordinates, that's how it is. But we are not going to take a look at the details because we don't care about the details this time. Okay, then once differentiating this one more time with respect to time, we will get acceleration. And now this acceleration is already, look at the monster how it is. You know, look at how many different acceleration components we have and how bad it is. Consider this too. This is the geometric representation, so it's not even a symbol representation, but matrix representation. So is this even real? Well, it is real, but you don't need to worry about that. Now, in acceleration, we have 5 different kind of accelerations. 5. Remember, in rigid bodies, we have 3. Rigid bodies, it's translational acceleration, normal acceleration, and tangential acceleration. Now, because of body is deformable, we have two additional acceleration components. Coriolis acceleration, because now particle can move in a rotating disk, and acceleration due to the deformation. So those are the two additional components. And now expressing that with help of generalized coordinates, this is how it looks. And now we're using coordinate or this mapping matrix, all becomes, this is how they all look like. This is going to be my inertial forces, which is a mass multiplied by acceleration. It's just that the acceleration is so painful component that the pain comes all over. But never mind. Finally, when I did my math, this is how my mass matrix started to look like. Of course, this is, by the way, a mistake. This should not be here because this is just a mass. Look, m equal to this. So this should be deleted here. And quadratic velocity vector, which, by the way, is the worst possible component ever. Ever. So it's really, really bad. That's how it reads. Now, finally, my mass matrix looks like this. So it consists of 6 different components. 6 different components. They are associated to translation of the reference coordinate system, rotation of the reference coordinate system, and modal coordinates. And then the coupling between these 3 items. Finally, when I look at the details of the mass matrix, these 6 components, they include components that are called mass invariants. And those are the components that remains constant during the computing, during the simulation. Now, those are the ones that combines how well my finite element model and multibody system dynamics are coupled together, surprisingly enough. Now, user typically can select which one out of these 9 components are keep active and which one of them are ignored. And now this is exactly that tells you how well is this coupled. Let me summarize. So these are how you can compute it. And now if you select them to be active or deactive, you can either have something that the finite element model is completely coupled with your multibody dynamics or completely decoupled. Completely decoupled, what that means? It means that body is rigid. Body is completely rigid. It's behaving like rigid body. And then you can have full coupling deformation. Of course, this is a picture, the screenshot from Atom software, and you can see those 9 in mass invariants, and the user can select which one of these should be active and which one of them should be deactive. This is a risky business, but this is a feature that most of the software are providing to users. They're saying you can select the one you wanted to keep it active and the one you wanted to deactive. Why they give this opportunity to user? Because this affects the computational efficiency quite a bit, but it affects the results as well. Now, the difficult thing is that, how you can select which one should be active and which one should be deactive. You really need to be years and years in this field to be able to do that. So my advice to you, keep them all active. Make this finite element model and multibody dynamics to be completely coupled. And that's the end of the story about the mass invariants. Let me summarize. Mass invariants are coupling deformation and reference motion. And you can make this coupling to be loose, completely decoupled, or full coupled. My recommendation is to keep it full coupled because sometimes you want to simulate things as a rigid bodies. You can try that. That kind of makes sense. But other options, this partly coupling makes no sense. Okay, so here's my final question to you. Role of mass invariance allows to describe structural damping, allows to describe external applied forces, couples the stiffness and damping, couples the finite element model and multibody system dynamics. Now, let me take this. Okay, so one student, can I just close this? Okay, what number? Well, how much is the success rate here? 95. Why not 100? Same. There's no difference. So next one. So then, what is this? This shouldn't be here. So roll of mass invariance. So this is my last question. Once you're done with that, then that's it. So. Okay, then we're gonna close for today. Okay, so 10, no, 9, 8, 7, 6, 3. Okay, well, are you curious to see if this is going to be 100% or not? No. What kind of attitude is that? You know, the number one lesson is this: can do attitude. That's the number one. Always can do attitude. So it's going to be 110%. 110. Okay. So 2 are okay. 1. So can we close here?
Yes.
Because the last time the one we did not got more than this. A bit scary, but let me see.
Yes.
Not good. No good. So it's all about the coupling between the finite element model and multi-body system dynamics. That is a role of mass imbalance. Okay, with that, let's close and let's see. And then the final thing, you want to see the questions. You will see next week. No. I'm gonna put this in model database tomorrow. Can I? Because I would like to leave early today.
Yes.
Can I? You give me a permission? I have your permission, right? Good. Thank you. So it's gonna be on tomorrow morning.
And when will we choose one question?
Yeah, you can choose one question, and it's all about who is the loudest. So I'm asking what's the question you want to have. And then you're yelling, number one, and it's going to be number 1. And what's the question you want to take it off? Then you call again, you're yelling, number one. And then I don't know what to do. Okay. See you guys on Monday. It's going to be the last lecture then. Take it easy.